Okay, we are starting our probability unit, and I want to kick this off by looking at an applet. It's called the Random Baby Applet. So go to Blackboard, and there's a link there, and I want to show you what the applet is doing. It is basically simulating a chance process. So we are placing 4 babies, and in this particular case, one of the 4 babies was placed in the correct house. So let me do it again. So you don't know which house the baby belongs to, and in this case the red baby was placed in the correct home. So I'll do this another time just to kind of get the gist of it. So it's presenting the number of successful placements. In this case, all 3 of them happen to be trials that resulted in 1 correct placement. Now let me do it one more time because I'm sure we'll get a different outcome here. Okay, we did not. Okay, I'm glad that happened because actually, do we have any knowledge about the next outcome? Just because we had 3 trials that resulted in 1 correct placement, did I know anything about the next placement? No, I did not. It's independent from the others. So that is actually a concept we're going to talk about today. But I felt like we probably should get something different that time. And again, 1 placement. Now I'm going to speed this up a little bit. And y'all can pause this and play around with it as much as you want. So you can see here, now I've done 9, 10, and then like 15 trials. And I never had a 3 outcome. Think about why that might be the case. Most frequently I had a 1, but I even had a 4 at a time. So I'm going to increase this to 100. So you kind of see what's happening there. So you can see the average is 1.035. It also shows it down here graphically. Now, the reason I'm doing this so many times, I'll even add 1,000 here, is because I want you to see what happens with the graph. That's the main thing I'm focusing on. The more times I repeat the process, the closer my experimental average gets to the theoretical average. So that's one of the concepts from this unit. So why is the theoretical average 1? Well, it's because the probability of placing a baby correctly is 0.25. So let's just talk about the blue baby for a second. So I'm placing the blue baby, and I don't know which house the blue baby goes in, and I just guess. So I have a 1 in 4 chance of getting that correct. And there are 4 homes, so it's going to be 1/4 of 4, which is just 1. So the average you would expect would be close to 1. And the more times I do this, the closer it gets to 1. Now it fluctuates because of the chance process, but it does get closer and closer to 1. Okay, so let's go to our notes and sort of fill in some of this. Okay, so what did you notice about the average number of successes as you repeat the process over and over? Well, the average gets closer to 1 successful baby delivery. Okay, so chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. So this is actually the law of large numbers. And it says that if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. So that's what we are observing in the graph that we were looking at. Okay, the next little section here. How do you interpret a probability? It is the long run relative frequency or sometimes referred to as the predicted relative frequency in a large number of trials. It's always between 0 and 1. 0 means impossible, and 1 means certain. So one thing I want to point out is to beware of scientific notation. So if your calculator ever gives you something like 3.5, first of all, you know if it's a probability, that's not possible. It cannot be bigger than 1. But usually what has happened is it's really something like this, 3.5 times 10 to the negative 3. That is possible. So just be careful to make sure that you notice and it shows up with an E in your calculator. Okay, chance behavior is unpredictable in the short run, but has a regular and predictable pattern in the long run. And that is a big concept for this unit. So we're going to do a little activity here. So the probability of getting a sum of 7 when rolling 2 dice is 1 in 6. Interpret this value. Okay, of all possible outcomes, 6 out of 36 outcomes have a sum of 7, and that is a theoretical probability. So if we actually repeated this, and rolled 2 dice and summed them up, we would definitely not get exactly 6 out of 36 to sum for 7. Now, if we repeated this many, many times, then it would approach the probability of 1 in 6. So, and that's because it's 6 over 36. So that just simplifies down. Now, where are we getting these probabilities in this table? So I want you to pause the video and think about it, and then check back in just a second, and I'll show you where these probabilities are coming from. Okay, so what I have here is basically just it's a little example as to how you can construct or determine the sample space for a chance process. So each of these represents one of the die. Okay, so I could get a 1 with a 1, the sum would be 2. I could get the first die with a 1, the second die with a 2, and that'd give me a 3. So there's a little pattern here. And then 4, 5, 6, 7, 8, and 9. I'm not going to fill all this in. It gets all the way down to 12. So there's only one possibility or one outcome out of all 36 that gives me a 12 for the sum, and it's over here. And there's only one that gives me a 2. So everything in between, obviously you can fill in the table and figure that out, but that is where that information is coming from. So I just want to make sure you understand that. And this is a probability distribution, and we've looked at these before, but just to review that. Now, we're going to do a little activity here. You're going to flip a coin. And I actually have my results. I want you to pause, and you're going to flip a coin. You're going to write down the results. You're going to flip it 50 times. And while you're doing that, I'm going to write down my results. Okay, so I flipped a coin 50 times, and I recorded. I have like 10 per row, just to kind of organize it. And I had 27 heads and 23 tails. And obviously, your results will be a little bit different. What I'm interested in figuring out, though, is how close are we getting to what we would expect to happen, which would be 25 and 25. So if you did this many times, you would expect that the proportion would get closer and closer to 0.5. So theoretically, we know the probability of getting ahead is 0.5. So we're comparing our theoretical probability to our experimental probability. So our experimental, this is theoretical, our experimental probability here is actually 27 out of 50. So it's a little bit more than 0.5. So if you repeated it many times, it would get closer and closer to 0.5. All right, so continuing on. So for mine, I noticed that mine was pretty close to what you would expect, but my probability of heads was a little bit higher. So what are some of the myths of randomness? So we talked about this a little bit earlier. I told you I actually violated or fell to the fate of one of the myths here a minute ago when I said that I expected to get something different than 0 or 1 baby to be delivered because I kept getting 1 baby. But actually, they were independent events. So what had just happened has no bearing on what's about to happen. So that's what we're going to talk about. So the law of averages, we all fall prey to this. It's just common nature. It's just human nature to do that. It's very common. So the law of averages is a myth which leads someone to expect a certain outcome based on a recent outcome. For example, if you toss a coin repeatedly and the last 4 tosses have resulted in a head, you would expect the next toss to be more likely to be a tail to average things out. We all know that the result of tossing a coin is independent of the results of prior tosses. So the myth is that future outcomes must make up for an imbalance like 6 straight tails. Of course, things do even out in the long run, and that is the law of large numbers in action. So the idea of probability is that randomness is predictable in the long run, and the myth of short-run regularity is that randomness is also predictable in the short run, which is a fallacy. The two myths are related, so just make sure you understand that the law of large numbers does apply in the long run, but the law of averages is a myth, so just make sure to not fall prey to that. Okay, so what is the purpose of simulation? So we're going to learn about simulation because, and we've actually already done a simulation. We use the little applet to do that. Okay, so simulation is used to estimate probabilities when they are difficult to calculate theoretically. So if we do not know what to expect from a chance process, we can use a simulation to at least have some understanding of the probabilities. So what are the 4 steps? So first you want to state the question of interest. What are you trying to figure out? You want to describe how to use a chance device to imitate one repetition of the process. Explain clearly how to identify the outcomes of the chance process and what variable to measure. And perform many repetitions of the simulation and use the results of your simulation to answer the question of interest. We are basically laying the foundation for inference here, so I just want to make sure you understand that. So we're going to do a little simulation on streakiness. So let's read about that. Suppose that a basketball player or a basketball announcer suggests that a certain player is streaky. That is, the announcer believes that if the player makes a shot, then he is more likely to make his next shot. As evidence, he points to a recent game where the player took 30 shots and had a streak of 7 made shots in a row. Is this evidence of streakiness, or could it have occurred simply by chance? Assuming this player makes 48% of his shots and the results of his shot don't depend on previous shots, how likely is it for the player to have a streak of 7 or more made shots in a row? So I want you to think about what this question is posing. But basically it's saying if his success rate is 48%, how often, just by chance, would he get 7 or more successes in a row if he is not streaky? So I know this is a strange term there. So we're going to use a coin to simulate this. And we're going to come together tomorrow in class and we're going to look at it, but I want you to follow the steps here. And you're basically going to simulate this process, this chance process. So just to get you started, use a coin. Let heads represent a made shot and tails will represent a missed shot. So you're going to flip a coin 30 times. And that is because he's claiming that in the recent game of 30 shots, he had a streak of 7 made shots. So what we're going to do is we're going to record the length of the longest streak of made shots. And you're going to repeat this 5 times. So, for example, The video is about to run out, so I'll just get you started. You'll do 30 tosses, and you want to record your longest streak.